This is our dynamics project, the Supercharger Lift Assist. I'm Chris DeCastro.
I'm Nick Skillen.
I'm Ellie Ferguson.
And I'm Rachel Johnson.
So some background for our project. The Eden Supercharger facility is located in Athens, Georgia. It is a manufacturing plant that produces devices that manipulate airflow in automotive engines to increase power. There are two new product lines that require a Gorbel bridge and G-Force lift assist. Through our research, we have found that G-Force technology fills the void between traditional lifting devices and completely automated robotic solutions. These devices use the human's intelligence and adaptability for guidance, but the work is done by the device. The benefits of using this crane are that it does not put stress on the building's overhead structure, and they don't require an existing support structure. Since we are to solve for the load rating capacity, we need to understand what exactly that means. According to Gorbel, rated capacity is the live load that can be lifted by the bridge system. The design load for the bridge system is based on the rated capacity plus the dead load of the bridge itself.
One of the new product lines at the Eaton Supercharger facility will use an end effector with a tare weight of 45 pounds and a capacity of 100 pounds, and the other product has a tare weight of 178 pounds and a capacity of 50 pounds. Our job is to solve for the loading rate of the yellow bridge and decide which size G-force is needed.
In order to find the load capacity of the yellow bridge and the correct size for the Gorbel G-force, we must take into account multiple different theories and equations of dynamics. The first equation of dynamics that we have to do is the kinematic equation v squared equals vi squared plus 2ad to find the acceleration of the G-force that carries the product weight. Later, we have to use Newton's second law to find the dynamic load on the G-force. And then we also have to use Newton's second law to find the load rating on the bridge. Lastly, we also have to analyze the entire system in static equilibrium to find the total design load for the bridge.
We obtained a chart from a Gorbel brochure and were able to determine the maximum lifting speeds when the device is fully loaded. We assumed that it was fully loaded so that we could obtain the maximum force due to acceleration. We also converted it from feet per minute to feet per second. And we found the maximum lifting range of each size G-force.
The G-force must be able to support the maximum load, so complete the calculations using the weight of product B because the product A is lighter.
We solve for the mass of product B by adding the tare weight of product B and its capacity to get 228 pounds, and we divided that number by the acceleration due to gravity, and we get a mass of 7.081 pound mass.
Because cost increases linearly with increasing loading rates, we want to select the smallest capacity G-force that can support the maximum load.
To solve for the acceleration of each size G-force, we end up using the kinematic equation, which states that the velocity squared is equal to the initial velocity squared plus 2 times the acceleration times the distance.
We can rearrange the equation previously mentioned to find the acceleration of the G-force. We obtain the values for the maximum lifting speed and the maximum lift range from a G-force quick facts chart. We also assume that the G-force begins at rest, and ultimately we achieve an acceleration of 0.1972 feet per second squared for the 165 pound capacity G-force.
Newton's second law is one principal equation used throughout this project.
For the 165-pound G-force, we use Newton's second law to take the sum of the vertical forces acting on the G-force. The resulting dynamic load from the acceleration of product B was determined to be 229.4 pounds. Because the maximum capacity load that this size G-force can support is 165 pounds, and 229.4 pounds exceeds that capacity, the 165-pound capacity size G-force is not large enough.
For the 330-pound G-force, we wanted to make sure it would be able to hold both product A and product B. So after summing the forces in the y direction for both of those products, it was found that it can hold both products.
As shown previously for the 165-pound capacity G-force, we performed a similar calculation for the acceleration of the 330-pound capacity G-force, which came out to be 0.07102 feet per second squared.
Now that the acceleration of the 330-pound G-force lift assist is determined, Newton's second law can be used. The summation of forces in the y direction equals the mass times the acceleration plus the mass times the acceleration due to gravity. We can find the summation of forces in the y direction by multiplying 7.081 pound mass by 0.07102 plus 32.2 to give a final summation of forces in the y direction of 228.51 pounds.
The dynamic load of 228.51 pounds is less than the 330-pound capacity size G-force. Therefore, this size G-force is a viable option.
As shown in the chart, the 330-pound G-force can support both products A and B. The 330, 660, and 1,320-pound G-forces are all viable options, but because cost increases linearly with the load rating, the best option is the 330-pound G-force.
The 330-pound G-force is the smallest capacity option that can support the maximum load. Therefore, it is the cheapest option.
For the product weights given, select the 330-pound capacity G-force.
Now, we will find the loading rate of the yellow bridge, which is displayed in this picture.
In order to find the load rating for the yellow bridge, you can sum the forces in the y direction, and it should be equal to the tension minus the weight of the G-force minus the weight of the bridge, all equal to the mass times the acceleration of the load.
Because the bridge must support a tension force of at least 559.23 pounds, we ruled out the 250 and 500 bridge series and selected the 1,000-pound capacity bridge.
The chart below, based on the 1,000-pound capacity, 20-foot span, and 14 feet underneath the bridge, shows how much easier Gorbel crane/bridges are to move and how much less dead weight they can carry than certain other crane types, assuming the weight of the yellow bridge is 326 pounds.
Now that we have determined the loading rate on the yellow bridge, we can solve for the total design load that the bridge must be able to support, including the weight of the bridge itself. Here, we are summing the vertical forces in a state of static equilibrium because the bridge is rigidly connected to the freestanding workstation. The resulting total load of the bridge is 885.23 pounds.
We found the final design load to be 885.23 pounds, which is less than the 1,000-pound load capacity, so this works out.